Okay, great. Yeah, thanks everyone for coming. So it's a great pleasure today to have Josh Fisher. So he started his career as an undergrad and then graduate student at UC Berkeley. We have actually a good, his advisor is also a good friend. So we started getting to know each other at the time. And he's worked a lot on first photosynthesis, carbon uptake from ecosystems and evapotranspiration, did a lot of nice work trying to bridge the gap between observations, especially at the eddy covariance sites, and then observations from space. And since then, he's been moving on. So he's been doing a lot of nice work. He's now also affiliated with Chapman University, and he's been really one of the pioneers of using space data, especially land surface temperature, and a lot of those things that we can use from space, including on the ISS, on the space shuttle, so that we could also observe the Earth's surface at a resolution that we've never achieved before. And so that's really telling us new things that we can learn from the land surface, especially related to evapotranspiration and carbon cycling. And so it's been really pushing the frontier in terms of how we can monitor and understand the Earth science, especially the land surface. So very much looking forward to your talk. Thanks.
Yeah. Thanks, Pierre. Yeah, Molly, I don't know if maybe you can just like hide the video or like scroll this up. Yeah. Maybe it'll get bigger. But while Molly's doing a little cinematography on this presentation, so just really quickly, just so I kind of know my audience a little bit, are you guys more like remote sensing-y people, more ecology people, more modeling, climate science, coding? Like, just shout out so I can kind of what you are.
Remote sensing.
Remote sensing. Okay.
Climate modeling.
Climate modeling. What about you guys? Climate modeling. Climate modeling. Climate modeling. A lot of modeling. What models do you guys use? Like, is it all one or different model?
Hierarchy, I guess.
Okay, cool. All right. Sounds good. Well, then I will definitely focus a bit on the modeling side as well as the remote sensing interface here. And so, all right. So our story begins in 1835 when Hans Christian Andersen wrote a children's story about a young lady whose royal identity is established by her physical sensitivity to a pea that was placed underneath her bed, covered by 20 mattresses and 20 feather beds. And in the morning, she lamented about the discomfort from the pea because only a real princess would have such a sensitivity, thus verifying her claims to royalty. Now, the land surface, our ecosystems of the planet, our forests, are very small relative to the whole Earth, right? Most of the Earth is atmosphere and ocean, but it exerts this enormous sensitivity and influence on Earth's climate as a whole. And so what we're trying to establish is what is the true sensitivity? Who can sense that the impact of ecosystems to climate and feedbacks? And what is the real royalty in the room? So if we think about our climate models, and here's our land surface model. There's land. Let's throw some weather at it, maybe some CO2, and up pops an ecosystem. And if you change any of those dials, you change the ecosystem, right? You change the water and carbon and energy cycling. But there are myriad processes wrapped up in this cartoon, right? We've got microns large pores on leaves. When open, allow the land surface to take up carbon. And when closed, stop taking up carbon. Also water through transpiration, influencing both water, energy, and climate at large. This is a nice animation I stole from National Geographic showing transpiration. We've got photosynthesis, which operates on electrons, but we're not representing all these biochemical reactions in climate models. So there's assumptions and uncertainties introduced on our assumptions about how these processes work at the leaf scale. And of course, not all leaves are created equally. We've got leaves that are bigger and shaded at the bottom of canopies and more sunlit at the top, and they get turned on and off by light differentially and heated up. And so we can actually see some of the temperature from space. And so this helps to constrain some of these processes that are hard to capture and represent. Now, initially in climate models, the land surface was put in not for its carbon and water cycles, but because land physically got in the way of the atmosphere. The atmospheric modelers needed to get their winds in and out and really put land in there for the aerodynamic resistances. And it wasn't later until we're like, oh, actually, they're useful for carbon too and water. And so intercepting wind, intercepting water, that would otherwise maybe go to the soil surface to turn on soil processes. And then how do we represent all the different species of plants on the planet, right? So they all are different for good cause, good reason, but we're not representing the thousands of species in climate models because that would be too computationally intensive. So we make assumptions and groupings that are human defined. And so how our human definitions create these groupings or these plant functional types significantly alters the trajectory of climate models because now you've got some plants that are growing fast, some plants that are going slow. Um, and then we've got nutrient uptake, constraining carbon uptake as well. And then how carbon gets allocated into wood and roots and leaves and exudates and other plant components. The climate models have to drop leaves at the right rate so that the leaves aren't on the canopy at all times and then suddenly fall off or never at all. And then they have to decompose at the rate. So when the leaves hit the floor, they don't instantly decompose, but they don't sit there forever. And so all these decomposition and respiration, soil respiration processes are done by bugs, ants, termites, worms, bacteria, but again, not represented in climate models. So these assumptions are made about how the termites respond to temperature or moisture, or how the bacteria respond, again, introducing uncertainties. And ultimately, there's a number of soil layers in which soil carbon and nutrients sit, and the more layers represented in the models, the more computational demand there is. How much carbon is stored in ecosystems is very important, especially as we are faced with increased droughts in which there's not photosynthesis, but plants are still able to survive because they have this stored sugar in their wood or in their roots. And so how long can a plant survive before it starves to death? And so ultimately, we're interested in the net carbon exchange between the land and the atmosphere. Are ecosystems a net carbon sink or are they net carbon source? And that really determines the feedback to climate change. Hydrologically, we want to capture snow melt. We can see the snow. It's hard to get the snow melt right. And then the water, as it infiltrates or percolates into deep groundwater or evaporates up to the soil, up to the atmosphere, along with transpiration for total evapotranspiration. We want to get the runoff right. And as the rivers are routed over the landscape in these kind of sinuous and changing dimensions, sometimes human altered, are those really captured in the coarse grid scales of climate models? And if not, what are the ramifications towards uncertainty? And ultimately, you want all the water balance components to add up. You don't want too much groundwater storing up. You don't want it all evaporating too much. So water balance is a key component to the land surface models. And I don't have a good picture of water balance, but I have this picture of this guy like balancing over water. So you can imagine water balance is important. Then there's more dynamic components, right? So if a tree falls in the forest, which plant functional type gets to occupy that gap? And as bioclimatic envelopes start to warm the northern hemisphere or warm higher altitudes, which plants get to establish those new niches? Which plants flee the Amazon up the Andes or go from the US into Canada? And how do they compete for space, for light, for nutrients, for water? And how do you kill a tree? This is actually a hard question to answer. Does it starve to death because it ran out of carbon? Does it overheat? Does it get attacked by bugs? Does it get consumed by fire, which has an anthropogenic human dimension? Getting that right, that balance right, is super critical in climate models. And then land surface also has other impacts for trace gases and aerosols. So you've got all these processes wrapped up into this cartoon, right? And you can see just explaining these processes, all these assumptions, which lead to uncertainties. And our models are getting more sophisticated, right? They're starting to look a little bit like video games where you've got some disturbance, and then you've got which ones compete for that space and recruitment, and then all of these alter water and energy and carbon cycling as best as possible. But even still, does this really capture the complexity of ecosystems? Because really, ecosystems look more like, less like that and more like this, right? with all these processes tied up in there. And this would be all well and good if that's all we had to do as ecosystem modelers, if all we had to do was get this right. But now we throw a wrench into this machinery, and this wrench looks like this. And you don't even have to put axes on this plot anymore for people to know what it is. It's so iconic. But of course, if there's students in the room, you got to put axes on your plots at all times. So it is the rise of atmospheric CO2. And so now we're seeing things we haven't seen for hundreds of thousands of years. Warming, CO2, rapid changes. And so getting that machinery right is all well and good, but now you throw this wrench into the machinery. And so that's why we have a lot of uncertainty in these models, right? So this is the famous Friedlichsen plot. And so the land carbon uptake, each of these models, or each of these lines is a different model from a different center, the UK model, the French model, the Australian model, US model. And so some models are saying, well, you know what, plants love CO2, and there's going to be more CO2 in the future. So ecosystems are going to be super happy. And other models are saying, wait, hold up, that CO2 is leading to more droughts, hotter temperatures, and plants hate droughts, and they're going to crash. And other models are like, well, maybe it's somewhere in between. And so the idea is that this paper was published in 2006. So the idea is that they should start to converge over time as model developments take place, as there's more convergence to observations. So then 10 years after that, Friedlichsen and colleagues looked at the models, and it looked like this. So basically that super big spread, slightly different color scheme. So, which isn't going to help anyone except maybe, fashion. But, the models are starting to converge. And so I kind of liken the modelers to the blind men and the elephant, right? Everyone's saying something different, but everyone's saying something kind of similar. And it's that which we cannot see, right? The elephant in the room, which is the future of the earth. But maybe if we start to kind of like piece these together and understand our representative biases, we can start to figure out what the true picture is. And so what are our biases? Here's a cartogram I made of where the model development is taking place, and it's where you can imagine in the rich countries, the US, in Europe, in China, in Australia. So that means our models are biased, right? Well, maybe not. But how would you go out and parameterize the photosynthesis sensitivity to soil moisture if you're developing that in model, or the nitrogen uptake? You'd go out and get data, right? And you would get data from your backyard. And so someone in Kansas is going to go in Kansas and get that, but someone in Japan is going to get it from somewhere else, and Australia is going to get it from somewhere else. And so there's this disagreement about the soil moisture sensitivity of photosynthesis because that's where the data came from. But there are still huge regions of the planet that are woefully underrepresented, right? So if we look at how well carbon space is sampled, and we look at just the land, right? There's a little bit more land in the northern hemisphere. This is the breathing of the biosphere, the GPP, the gross primary productivity, the photosynthesis. Most of that are in like the lungs of the planet in the tropics. But there's actually two poles of the carbon cycle, right? We've got a lot of carbon locked up in the rainforest, but we also have just a whole bunch of carbon locked up in the Arctic and boreal region. How is that possible, right? It's not these big majestic trees in the Arctic like there are in the tropics. It's these kind of shrubby mosses and grasses. But they live and they die, and it's too cold for bacteria and worms and termites to decompose them. So that carbon sits, and then it gets locked up in a new layer of permafrost, and locked up again, and locked up again. So now there's thousands of years of locked up mossy shrub stuff in the Arctic that's now being exposed as the permafrost thaws. So again, how good is our representation of our in situ measurements when we come to our biases? These are our flux towers, one representative of how we measure, ecosystem properties, and they're where you imagine, mostly in the US and Europe. And so woefully undersampling the tropics and huge parts of the Arctic. So we just came off a 10-year campaign in the Arctic that I was the modeling lead for, called Above. And that was really designed to go out and capture data that was underrepresented in the Arctic. And so we went out there, but still, it was NASA. We could only really operate in the US and in Alaska. Siberia, completely underrepresented. But great job for getting more data. But still, what do we do about this? And the tropics were missed. So that's where we come to remote sensing, right? We're in this golden age of remote sensing where we can now see every component of the water cycle. We can see a whole bunch of components of the carbon cycle, nutrients, biodiversity. And so now how do we interface that with the models? So when I first came to NASA, before I was at Chapman University and Hydrosat, my company, I developed a program called Change. This was when Obama was president. He had this whole change slogan. So I was like, oh, I got to have my own change thing. And so I'm really looking at how water, carbon, and nutrients interact with climate and how climate feeds back from an ecosystem standpoint. And so let's take kind of the crown jewel of ecosystems, the Amazon rainforest. It's the, considered the lungs of the planet or the heartbeat of the planet, exerts global influence on water, energy, carbon cycling, home to the greatest biodiversity on the planet. So the question is, well, what's going to happen to the lungs of the planet in the future under climate change? And some of the early models projected that the Amazon forest would die back under climate carbon cycle projections. Big worry, right? Lungs of the planet. But just a model. And so in 2005, the biggest drought in the history of our records hit the Amazon. And so the scientists were like, this is great. I mean, it was terrible, but it was great because these models were projecting more droughts into the future. So now we could see, well, how resilient was the Amazon? Or did it just like kill over and die? And so one of the earliest papers that came out from this '05 drought suggested that the Amazon greened up, and they came out with high profile papers on science and so on. And so this didn't quite make any sense, but they argued, you know what, there was less rainfall, but there were fewer clouds, which meant there was more sunlight. And they said there's probably still plenty of soil moisture. And with the more sunlight, the plants could photosynthesize more. And so they argued that perhaps it greened up. But our team was like, that's a little bit weird. And so we looked at this again using the Tropical Rainfall Measuring Mission, TRMM, for the rainfall. And then my PhD work with Dennis Baldacchi involved evapotranspiration. I was really interested in ET. And so I built these like sap flow sensors that you could stick into trees to measure transpiration. And I put them under eddy covariance towers to scale it up to the tower. And then I started scaling that from the in situ and towers to drones and airplanes and spaceborne measurements. And so then in my PhD work, I was one of the first people to develop a global remote sensing evapotranspiration product. And so we use this to look at, all right, we know there's a rainfall deficit, but if there was not a lot of evapotranspiration, there could be a lot of soil moisture. But if there was a lot of evapotranspiration, then you would have dry soils. So we put those together, and if you look at the rainfall record kind of right before this '05 drought, it drops there. But how dry was the soil? And once you put the evapotranspiration on, sucking that water out of the soil, you can start to see this cumulative water deficit, these days in which the ET was really drying out the soil. And so you can see this big peak in '97 and '01, those were El Nino years. And then again in '05, right, that drought, that was from the warming of the North Atlantic, which is kind of apropos now with these giant heat waves in Europe and in here. Um, so this peak kind of shows you how droughty the Amazon was, and that peak would vary around the Amazon depending on rainfall and evapotranspiration patterns. But the next question is, were trees dying? How do you figure that out? You couldn't figure that out from space. And so we had this long-term census network of plots throughout the Amazon where we knew how many trees were in this plot. So when the '05 drought hit, we went out and recensused the plots to figure out how many trees died, and then we correlated that with the drought intensity that we were measuring. And so what we found was that as that orange peak increased, whereas drought increased, you had more trees dying, right? Drought equals tree death. Not super exciting, drought equals tree death. But remember, right, those other guys said the Amazon forest greened up in the '05 drought. So now you have a paper in Science from us that said, well, trees were dying. And you had a paper in Science that said things were getting greener. So like, what gives? And so after we published our paper, some of these guys kind of broke ranks and reanalyzed their data and figured out, in the drought, there's actually a lot more fires too. And they kind of didn't account for that. And so the aerosols and smoke were kind of interfering with the NDVI, the greenness signal, and they reanalyzed their data. And instead of their first papers that said the Amazon forest greened up in the '05 drought, they had a new paper that said the Amazon forest did not green up in the '05 drought. So, kind of this back and forth in science. It's, what I call like nerd gang warfare. But it's still like important, right? Because we want to know what's going to happen to the lungs of the planet. And there's been scores of papers since then really trying to figure it out. But again, these models are projecting more droughts, more frequent, bigger, more intense. Just projections, right? So since then, we had something else that was better than NDVI and greenness, which was solar-induced chlorophyll fluorescence. This light that's emitted by plants when they're photosynthesizing or not when they're not. And so that could really tell you a lot more insight into just like if they were green or not. And so we had developed at NASA the carbon monitoring system where we started combining all these measurements together and models to constrain the carbon cycle. Now, I told you that '05 was the worst drought in the history of records. In 5 years after that, in 2010, an even worse drought hit the Amazon. 5 years after that, an even worse drought hit the Amazon. And it keeps happening. So now these red lines are kind of like the drought index, and they're getting worse and worse and worse. And so these projections that these models came up with of more droughts, more frequent, intense droughts aren't projections anymore. They're reality. And they're happening so frequently that the Amazon rainforest can, take a hit and those trees can die and then regrow, but it's happening so fast that they can't recover. And so we had a paper in Nature that kind of talked about their lack of ability to recover because these droughts are happening so fast. We had another paper in Nature that made the cover in Nature a few years ago using temperature measurements across the tropics and starting to see that the canopies were getting so hot, just starting to get so hot that photosynthesis was shutting down in massive scales. Quite worrisome. All right, I want to return to this CO2 curve and put it in the context of photosynthesis, the equation of photosynthesis, which is this, right? So where does that red line go? It goes kind of right there. And so let's say you have plenty of light, and let's say you have plenty of water. Does that mean you'll have kind of this infinite rise in biomass? If CO2 doesn't stop increasing, does that mean your biomass doesn't stop increasing? And that's what the early climate models said, is that, yeah, we're just going to put CO2 in and biomass comes out. But it was actually kind of ridiculous because there were so many petagrams and petagrams of carbon in biomass that you actually didn't have anywhere to put all these trees. It would be so much. Finally, someone's like, wait, what does this mean? And then they're like, oh, it actually means that like when you exit your apartment in the morning, there would be like a tree like on your mailbox, on your car, like just trees everywhere because you have to put that carbon everywhere. And so that didn't really make sense. And it was because the early climate models were missing a significant process, and that was nutrients. And so this is a nice figure by Victor Leshik out of Northern Arizona University, showing as we kind of have all this CO2 sludge on the planet, some of it can be diverted to plants, but not infinite. There are these knobs and controls by the major ecosystem nutrients of phosphorus and nitrogen. And so a little over 10 years ago, I asked the modeling groups of the world, what are you going to work on over the next 5 years? And you can see this word cloud shows that nitrogen was the big thing that they were going to work on, as well as fire and land use and hydrology, disturbance, and so on. And so now almost all the climate models have a nitrogen cycle in, and a lot of them have phosphorus cycling in. And so one of the big reasons we were looking at nutrients, again, is as CO2 rises, at what point do ecosystems stop taking up CO2 because they've run out of nutrients? And we can use the free air CO2 experiments, enrichment experiments, FACE experiments, where there's these rings. Do you guys know the FACE experiments at all? So these rings have CO2 pipes, and they kind of pump CO2 at elevated amounts onto the trees, and then we see like how much they can take up over a certain amount of time. And what we were finding is that as ecosystems ran out of nutrients, they stopped taking up CO2. However, there were some of these experiments that were running out of nutrients and kept taking up CO2. And we could not figure this out for like years. And it turns out, skip this, that if you're a tree species, different tree species, you will have the symbiotic relationship with a mycorrhizal fungal type, either arbuscular mycorrhizal or ectomycorrhizal fungi. And it turned out that the experiments in which they were running out of nutrients, but still taking up CO2. Those ecosystems were associated with one mycorrhizal fungal type that was going out well beyond the experiment, grabbing nutrients, bringing it back to the plants, and giving it to the trees. So they could, and then in exchange, the trees would pay them in sugar, in carbon. And so there's these different costs that the AM versus ECM fungi charge to the trees. It's this whole below ground economy, and the costs fluctuate. But that was basically explaining how nutrients modulated the ability of ecosystems to take up carbon. Now, that's all well and good, but we cannot see these fungi, right? They're like underground. So if we knew where they were, we could say, oh, that area will continue to take up carbon in the future. That area will probably start to run out of nutrients. So it turns out that if you're a unique tree species, you will associate with one type of fungi. And if you're another tree species, you'll associate with that other. So it's kind of a one-to-one. So you'll have completely different tree species that will associate with AM and other tree species that'll associate with ECM. And it turns out that tree species, totally different tree species that are associated with one mycorrhizal fungi type behave more similarly to each other than the tree species that are associated with the other mycorrhizal fungal type. So it's kind of like your fingers on your hand, each with a unique fingerprint, but those on your left hand behave more similarly in concert with each other than those on your right hand. And we're starting to pick that up from remote sensing. It's kind of like they pulse the trees in unique ways that are in common with each other. And so we can see that using remote sensing, both spaceborne as well as airborne hyperspectral. So we can now see the fingers of the puppets. Even though you cannot see the fingers of a puppet, you know they're there by how the puppet behaves. So we started putting this into the models, and one of the models that I built for the UK climate model was a nutrient or a nitrogen model, now with phosphorus. Lots of math and ecology in it. I think the most important thing that I want you to get from this is that I came up with a clever acronym for it, and it was called FUN, Fixation Uptake Nutrients. So I'm literally making climate modeling more fun. But now we have these dynamics in the models. And so I also went out and collected data in the Amazon. This is at the top of the Andes, looking out towards the Atlantic across Peru and Brazil, across the Amazon. And I led a nutrient fertilization experiment there for many years, putting down nitrogen and phosphorus and collecting soils and collecting leaves off the face of the Andes, which was not easy to do, all in the name of science. And so now we have these processes in models. So I initially built that in the UK land surface model. Jules brought it over to CLM, now in ELM. It's in NoMP and one of the LPJs as well. But now you can see how much nitrogen or phosphorus is being taken up by plants through mycorrhizal fungi or directly through roots or through symbiotic fixation or resorbed retranslocated from leaves. So these cool like ecological processes now have math behind it with assumptions, uncertainties, and also observational constraints. So started using remote sensing to look at how nutrient limited were ecosystems, basically using the evapotranspiration work of my PhD. So where you have a lot of water and energy, you have a lot of evapotranspiration. And you should have a lot of greenness too, like, right? The Amazon. There are two cases in which you can have a lot of water and energy, but not a lot of greenness. One is where you chop down the greenness. So like in the Amazon, you chop down, still lots of water and energy, not a lot of greenness because you chopped it down. Or two is where you don't have enough nutrients. So it's not getting as green as it could be. So putting some observational constraints on these processes that we put into land surface models. All right, so if we look at our total CO2 uptake uncertainty, most of that's in the land. The ocean models are pretty well in agreement in terms of how CO2 diffuses into the ocean. There's definitely some uncertainty in terms of biological pump, but most of that uncertainty is on land. So what is it about is it the nutrients? Well, most of the models actually agree if you don't have a lot of nutrients, then you don't have a lot of carbon uptake. Well, what about land use? The models also agree if you chop down forests, you don't have a lot of carbon uptake. What about climate? A little bit more disagreement, right? If you change temperature and rainfall patterns, you have some disagreement. Actually, the largest source of uncertainty of CO2 uptake is from the CO2 itself. If you change CO2 by just like a couple parts per million, that's when the models wildly diverge. That's when some models are like, all hell is going to break loose, and other models are, oh, plants are going to have a giant party. And so that's the big uncertainty. And most of that is in the tropics, right? The lungs of the planet. So now, we could just run these face experiments in the tropics, right? But they're very expensive to do. This is in like Tennessee somewhere. You know, you need a lot of infrastructure to bring this in, to pump CO2 in. You could basically count the number of trees on your hand in these rings. And, you know, tropical ecosystems are a lot more biodiverse. So you'd want to expand those rings considerably. You'd want to run it for more than just a few years. So the cost to run a tropical face experiment that would be needed to really constrain climate models, something that's big, something that's long term, would be billions of dollars actually. So like very unlikely. And you want to get that long time scale too, because these plants will, you know, change their compositions. Some species will outcompete the others, and so oftentimes the face experiments operate on like 3-year NSF funding cycles, and so this has been a big problem. And actually, this has been a big impediment to the uncertainty of climate models, right? We know that tropical CO2 fertilization is this huge uncertainty. We know what we could do if we had billions of dollars, but we don't. So we've just been stuck. And that has been like the sticking point for land surface models. So like end of science, right? I took you to the ledge, end of science. And then we just go home and cry, right? Well, so like how do you overcome this barrier? How do you overcome barriers in science? And sometimes the solutions to disciplinary barriers come at interdisciplinary intersections. And so you might have thought you were hearing an ecology talk. We're now going to turn to volcanology. So we often think of volcanoes as that like majestic peak in the background, right? With magma spewing out and National Geographic, right? That's what I thought as an ecologist. But it turns out that the volcanic complex extends for miles beyond the peak crater into the lowland forest below. And so if we think about like a landscape before a volcano erupts, and then thousands of years ago, you know, the volcano is formed, there's these cracks and fissures in the landscape. And CO2 comes out of these cracks continuously, forever, until the volcano dies, goes extinct, you know, after thousands of years. And it comes out in thousands of parts per million, uh, thousands of ppm of CO2, lethally high, nothing that we would care about as ecologists or climate scientists. But then it diffuses, you know, to background conditions. But it's along this diffusion gradient that is the future of the planet, right? So we're right now in the 400 range, but soon in the 500 range, sooner than we think in the 700 range. And so these parts of the ecosystem are now living in a future world. They're living in a world in which there's going to be more CO2. So the question is, what have they done? How much carbon did they take up? What are their species? Did they change their evapotranspiration? You know, what's going on? And so Mother Nature has basically put this face experiment for us, and we have to go in there and get figure out what the answer is. Also, the CO2, the isotopic signature of volcanic CO2 is slightly different than background atmospheric CO2. So if you're a tree that's breathed in volcanic CO2, your wood isotopic signature now resembles volcanic the volcanic CO2 isotopic signature. So for the past 10 years or so, I've been working in this range of rainforest throughout Costa Rica around these volcanoes, really kind of figuring out where these cracks and fissures are in the landscape and what are the ecosystems. So, you know, the question is like, is the crystal ball to the future of the planet hidden in the jungles of these volcanoes, which are hard to work in, right? This is a picture of me and my team leading some students through this like mud swamp in search of some of these CO2 vents. And sometimes you look on a map and you're trying to go from point A to point B, but you don't realize that you're actually in this like lava tube and you can't actually get there. So, I figured like rainforests, jungles are hard to work in, volcanoes are hard to work in. Maybe I'll put them together and they'll cancel each other out, but that was not the case. Um, so I took this picture of this beautiful double rainbow because it was a pretty rainbow, and then I realized, oh, actually, this is one of the CO2 vents right here. And so now the question is like, is the CO2 going into these trees and making them bigger, or like what's going on? And if you hike into this area, you can start to kind of imagine that the leaves are bathed in this elevated CO2. And so you can see there's this kind
Here
of
we have a little
volcancito, this
volcancito
crack and fissure that I
coming
found.
out. Giving us
And I
a
put
very
one of the
good
CO2
plan.
sensors in. You can see it's almost 900 parts per million at this time.
Here.
And you can actually see it bubbling out
CO2
continuously,
coming out with bubbles.
now going into the ecosystem. So this is those
And we
pipes that
are
I showed you
sampling
before in
the
Tennessee, but
soil.
Mother Nature has put this pipe here for us. And so my team's out there collecting soils and leaves. We're also now putting CO2 sensors in drones, in the nose cones of drones, and flying them over the treetops to sniff out the CO2 leaks. So we don't have to trek through mud swamps and figure out where they are in the landscape. And so here's one of our drones kind of flying over our sites, going in to sniff out the CO2 leaks. So now we can get the CO2 locations. And so the next question is, what are the ecosystems doing? And so there's multiple lenses on ecosystems that you have to answer to really understand ecosystems as a whole. Are they getting bigger? Are they denser? Are they taller? Um, the structure. Are the species changing? Or is the canopy chemistry changing? The composition, the traits, the water cycling, the carbon cycling, and like RGB lenses where they each kind of tell you the world in a different color. And when you put them together, it tells you the true picture. This is kind of like the lenses for ecosystems that when you put them together, spotlit by CO2, it starts to show you the true picture. Now, I'm using volcanology as a tool to answer my ecology questions, but it turns out that the volcanologists are very interested in ecology to answer their own science questions. And their science questions tend to revolve around like big disasters. When's the next big eruption? And so basically what happens is that as the magma starts to rise before a big eruption, it pushes CO2 up ahead of it, sometimes years ahead of it. And so volcanologists instrument volcanoes with CO2 sensors because they want to figure out the baseline CO2 signal and then the anomaly against it. But they need a long-term record of CO2. Uh, these CO2 sensors are very expensive often. They get damaged or vandalized or they're in the wrong places. And so they often lack their CO2 measurements to monitor the volcanoes. And now I'm coming along and saying, you know what? I've got your CO2 sensors and I've got thousands of them, and they're called trees. And they're great data loggers. They last way longer than your Lycors. They'll last hundreds of years. So now we've got kind of two communities that have not really interacted that much before. The ecology and the volcanology community. And I stole this graphic from the gravitational waves community, where now when they intersect, you have new knowledge of the universe or new knowledge of how the world might work. All right, last node of the change diagram, water, right? This is the big one for us humans. Um, we want to be able to grow food, right? We need water to grow food. And there's uncertainty associated with our water availability, associated with uncertainty in rain and snow and evapotranspiration and soil moisture and the groundwater change and our runoff. But we can now see from space every component of the water cycle. So I told you about TRIM before that has now evolved into the Global Precipitation Measurement Constellation across agencies. For snow, we can see snow, but it's still hard to kind of tell the snow depth or the snow water equivalent. You can do it from airborne LiDAR. My friend Tom Painter flies his planes over mountains before it snows with LiDAR, and then after it snows, and you can see that surface change and also hyperspectral to look at albedo and melt rates. Still hard to do from space, though. And that might change over the next decade. I'm leading a component to NASA's decadal survey for hydrology. And I think Pierre is part of that too. I think you were part of one of those groups. And Alex Konings and a lot of our buddies are in this trying to figure out what's needed by NASA over the next decade. For deep groundwater, have you guys heard of GRACE, the GRACE satellites? Super cool. They respond to changes in gravity. So what causes gravity? Mass. And so they fly over the Earth, and if there's a whole bunch of groundwater, there's a lot of mass, and they get pooled stronger. And if the next time they fly over and there's a big drought or we've pumped all the groundwater out, there'll be less mass. And so they'll be sensitive to that change. So they can actually detect groundwater change by changes in just mass of the Earth associated with groundwater. We can now see river discharge based on like the height of rivers, and that's from the SWAT mission launched, I think last year or a couple of years ago. And then soil moisture. This was actually the mission that originally hired me at NASA, the SMAT mission. It had a radar that like sent this radar signal into the soil, bounced back, and basically told us how wet or dry the soil was. That has since broken. Now it just uses light reflectance. And just recently, NISAR was launched with the Indians to really step up the radar game for soil moisture. For evapotranspiration, this started becoming my thing. I proposed a mission to NASA as the science lead with Simon Hook, the PI, and we really wanted to figure out what was evapotranspiration at those scales that was needed, that high resolution, to capture all the agriculture, and frequent as water changed throughout the week. And so here's a video that we put together at JPL before we launched. Hopefully it works. We're interested in our ability to sustain food production. We're interested in our ecosystem health. And that's all tied to water. How much water our plants, our crops need, we want to know. And as water resources become more uncertain, more variable, we need to really track that really precisely. We can't just guess anymore.
So eco-stress is going to measure the surface temperature, and then we're going to use that surface temperature to be able to determine how much water the plants that we're looking at are using.
We'd like to show how we can use eco-stress data to optimize agricultural water use.
Eco-stress is an instrument that's going to go on the International Space Station. It stands for the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station.
It focuses on how much water plants use all over the planet and how much water plants need, and if there's stress, water stress or heat stress that plants are facing.
We can measure the surface temperature of the Earth within a few tenths of a degree, and then we can use that information to look at objects on the surface of the Earth, and in this particular case we're interested in looking at plants.
Plants, as they start to suffer from heat or water stress, they begin to heat up in a similar way to a human with a fever. We can pick up that stress before the plant is visibly affected. So there's this window where water resource management and agricultural users can actually allocate more water before they die, before the damage is irreparable.
The space station is going to fly over at different times to be able to look at how the stress is changing through the day and allow us to characterize vegetation in ways that we've never been able to characterize it before. The instrument itself is looking down at the surface of the Earth, and it uses a mirror that rotates to scan across the surface. This measurement's being made in microseconds, but it's enough time for us to measure the energy that's coming off it and then translate that energy into a temperature.
The temperature measurements from EcoStress can detect volcanoes. We can detect urban heat from cities.
So although we're focused primarily on looking at plants and making sure that we can maximize the amount of food that we can get back for the water that we use, the mission can be used for many other purposes. What hasn't been possible in the past is to make the measurements as frequently as we need to make them with sufficient detail, and it's that combination that is so important. And really that's just a reflection of the improvements in technology.
Our ability to sustain livelihoods, food production, ecosystems, and the health of the planet through EcoStress data is invaluable. So we launched the space station. This was our designated plot of land, so to speak, or at the end of the cul-de-sac. You can see that there's a number of these boxes like EcoStress plugged in. It's like giant USB ports. They all have different kind of characteristics, but they all plug in the same way. That's how the space station operates. And one of the astronauts did a 6-hour spacewalk before our launch to set up the data communications for us. It was a beautiful launch right as the sun was rising, and you can kind of see the final stage separation of the payload from the rocket separate with EcoStress right there as the Earth came into view. So in the meantime, we had started using Landsat, another satellite to get out of evapotranspiration, and started developing a lot of tools that end users could connect with the data. So you didn't have to be a PhD scientist or some sort of coder. You could just access it on a GUI, some API, a website. And so now we're starting to make these bridges between the data and the science, the technology, and the end users, the farmers, the water managers. I've been working with state governments, including the state of New Mexico, water managers, and it's really revolutionizing how they work and how they change or how they allocate water. So a lot of my tools now involve, in addition to science and engineering, I'm employing a lot of artists and designers as that key bridge to figuring out how end users will interact with data, human-centered design, UI, UX. And so, and also starting to employ these in my own teaching techniques. So making all my teaching materials freely available. I can now I figured out how to basically teach teenagers as young as 13 within a week to be able to download eco-stress data, track some climate disaster, make a map, and like send it to NASA. And so what's really interesting is that I'm trying to accelerate the pace of our ability to solve climate change, to keep up with the pace of climate change itself. And what's interesting is that it's also creating an identity of scientists at a very early age to historically excluded demographics. And so what we're also seeing is that that the diversity, equity, inclusion of the geosciences, which is historically the least diverse of all the sciences, is now increasing because of pedagogical techniques of creating identity and independence and access to the data in science. I'm also teaching community members in environmental justice communities how to access the data and advocate for themselves. I've been working a lot in Southeast Los Angeles, near where I live, and they're looking at urban heat inequities. We're finding that parks that were put in Southeast LA are way hotter than parks that were put in the more affluent West LA. And so now policymakers are starting to see our papers, and they're coming down from the governor's office to basically say, do you see that paper by that group? We're going to have to deal with it. Also starting to make the data more accessible to firefighters. That's a big issue where I am in California as well as worldwide, and starting to figure out how to help firefighters, fire chiefs, and captains make decisions faster and more accurate, given this wealth of data that's coming online from satellites, drones, balloons, and so on. And we're actually attaching these thermal sensors to balloons and launching them over fires so they hover. And so you can see every single tree, if it's on fire or not, the tree next to it, how drought stressed it is, which will indicate if the fire is more likely to move into that tree or not. And we have a communications relay on the balloons that sends it directly to the firefighters in the field where they often don't have communications. So really advancing the fire landscape as well. So I mentioned that I have a company now, and so this was spun off from JPL, and I'm the science lead. I wasn't the founder. The founder, Jacob Van Zyl, kind of saw the writing on the wall, which was we had launched some kind of low-cost thermal technology to Mars, and he was like, you know what, we should get this on Earth, but if we start to go through the classic NASA paradigm of proposing missions, it's going to take forever, with government shutdowns and congressional budget fights. And of course, hindsight is 2020, and he was absolutely right. So he spun it off as a commercial company, and we've already launched 2 satellites. We're en route to a 16 satellite constellation where we're getting down to 25-meter resolution every day. And so unprecedented data. I joined Hydrosat. When I was interested in joining Hydrosat because I was like, wait a second, you guys are actually doing technology more advanced than what we're doing at NASA and ESA worldwide. And if I want to be like the most cutting edge science in this field, I got to be where it's at. And it just happened to not be at NASA anymore, although we have NASA origins. But the commercial space industry is absolutely booming, and I did not realize that. I don't know how many people do remote sensing here. Everybody kind of knows MODIS and Landsat and VIIRS and Sentinel, but when we launched our first satellite on a SpaceX rocket, there were over 100 other satellites on that from the commercial space industry across radar and hyperspectral and microwave and so on. And so the space industry is absolutely booming. And if you're going to be involved in remote sensing, you have to be clued in on this, because that is where the absolute future is going to be. And this is beyond politics right now. The Trump administration, Congress really wants NASA to engage a lot with industry, and that will probably continue post-Trump under whatever makeup of president and Congress that we see in the U.S. We're seeing this in Europe and worldwide too. Oh yeah, so this was our launch on one of the SpaceX rockets. Have you guys ever seen a rocket launch? Yeah. Have you seen a SpaceX rocket launch? And like, have you seen it like re-land its stage, which is like totally trippy because it's like watching reality in rewind. So yeah, this is it with the camera. So that was the stage that's going back to Earth, and now the camera splits, and so we're gonna see that was the fairing, so like a protective air piece. Now this one's landing back on Earth, and this one's going out to orbit around Earth, and then it'll start to shoot out those CubeSats, those small satellites, including Hydrosat. Right, so this is it now landing back on Earth. And it's almost like watching it in someone hit rewind, but it's real. Weird, right? All right, so now this one's going to start to shoot out the CubeSats.
Yeah, I'm 7.
We're the next one after that, in different orbits. So now we're like increasing the frequency of the thermal data, and our primary commercial customer is agriculture. So we now at 4 in the morning, we deliver our data through our app to over 4 million acres across the world, across over 70 countries. This is always changing. And basically, you're a farmer. In the morning, you get up on your tractor, you go onto the app, and it says, oh, that part of my field is hotter than the rest. I need to irrigate it more. And we tell them how much to irrigate. And so we can optimize the amount of irrigation, which saves water, increases food production, and allows them to use the water to grow new fields or to just save the water. So it's working really well. And now they're telling their friends about it. And we're growing super rapidly. We just closed our Series B round of $60 million. We make millions of dollars every year. But the data are free to academics. So, all right, the last thing I want to talk about really quickly is that's all well and good when you have water to manage, but what happens when you have no water to manage? That's when you have these massive famines. And so, like the UN World Food Program that, kind of assists on famine assistance, needs like 3 to 6 months of lead time to be able to help support millions of people impacted by famines. But how do you do that? Like a lot of our famine early warning systems miss these. Well, I told you that the Soil and Moisture Active Passive mission was the first mission to hire me at NASA, and led by one of my PhD students, Krishnamurthy, using tipping point statistical theory and soil moisture, we can now predict every food crash on the planet before it occurs, 3 to 6 months before it occurs. So, skipping through that, now the UN super interested. We just got $1 million like last week from NASA to operationalize this with the UN. And my university put it on the cover, but they think this is going to actually save millions of lives. So super excited about this. We just got the $1 million like last week. We're just kicking this off, and we're excited to operationalize this with the UN and move it forward. Oh yeah, okay. So that's pretty much everything I wanted to cover. I'm going to leave you with one last video, because if you couldn't tell by now, I love videos and like rock and roll music with the videos. So I'm going to leave you with one last video, and it was. All right, this is the EcoStress launch. So I told you we launched to the space station, but the space station's going 17,000 miles per hour around the Earth. So you can't just launch to the space station. You have to launch, and then it takes about 3 days of this dance between the Dragon payload and the space station before you dock. So then we dock to the space station, and then the Canadian robotic arm goes in, grabs EcoStress, pulls it out, passes it over to the Japanese robotic arm, and we got installed on the Japanese part of the International Space Station, very international. And that whole extraction installation takes 9 hours. But I have footage as seen by the astronauts of this like rendezvous and extraction, which I got, and I sped up to like 60 seconds with some rock and roll music. You guys want to see that? All right, there it goes.
Falling too fast to prepare for this. Tripping in the world could be dangerous. Everybody circling as vultures. Negative, nepotist. Everybody waiting for the fall of man. Everybody praying for the end of times. Everybody hoping they could be the one. I was born to run, I was born for this. Whip, run me like a racehorse. Pull me like a ripcord. Break me down and build me up. I wanna be the slip. Word upon your lip. Rather that you rip. Break me down and build me up. Whatever it takes. Takes.
Oh, that's pretty cool, huh? So that concludes my story of the Princess and the Pea, or the Earth's biosphere in the climate. And we're really striving to know that true sensitivity, that true detection, that true modeling capability. Because ultimately we all have the same objective, which is to live happily ever after. Thank you.
Thanks a lot, Josh, for the great talk. So maybe we open up for questions, starting with the junior scientists first.
Yeah, feel free to pepper me with questions. Could be any of the science that I gave all of like 3 seconds of attention to, or my journey, for those who are interested in like, oh, do I go into academia or industry or government or just
video creation.
yeah, or like what's next on my rock and roll music playlist. Yeah. Anything.
Yeah, so during that one part when you mentioned that there was, the paper that was already out there that was talking, and you did research that kind of conflicted it, and then it caused them to rethink their actions and, change it. I was just curious what you thought about that, like, how that was for you, I guess, a little bit personally. Like, did you face a lot of self-doubt, like, wow, I'm going out here into something that is completely unknown, and I'm like going to tell the other researchers that they're wrong? Like, I was just curious about like how that journey was for you.
Yeah, it was interesting because I was earlier in my career when that happened, and you don't know how to like necessarily, the politics or like who's friends with who. But I remember one time, like, it was like we were at a conference, and like me and my crew that had done it were like walking down a hallway, and suddenly the crew that had done the other paper were walking down the other hallway, and we just like kind of like stiffened up a little bit. And like that other crew was I think it was like Ranga Mainini's crew. Pierre, my name. He was at Boston University. He would wear like all black, and it was like postdocs wear all black. They were coming out like super like tough looking, but then everyone's just friends and colleagues in the end. Everyone's really just trying to figure out what the science is, and so there can be a lot of kind of antagonism and hostility in science from scientists to each other, right? Your paper sucked. You don't know what you're doing, blah, blah, blah. But you can easily change that. And like you see this all the time from your reviews, from your papers. You get reviewer 2, right? Reviewer classic 2. You're just like, you don't know what you're doing. This is bullshit, like whatever. And when you're a reviewer, you just have to get into that mind frame of I got to attack everything. And the more papers you review, you start to realize, oh, I'm starting to become that a-hole too. And so what I do is that I'll write my review, be very nitpicky, and then I'll rewrite it to be a lot more like collegial and like nice. And so it's really up to us in terms of how we treat science and our fellow scientists. Yeah, we have a lot of attacks on us, so we're coming together a lot more. But even in industry, like there are other companies that we compete with, and normally in commercial industry, you would be very cutthroat against other businesses. But I, as a scientist, I'm like, those guys are doing a good job too. Let's come together. Let's work together. Or let's like, I'll talk to those guys, but like, we're gonna compete and get this. If we can come together, that'd be great. But I'll give them shout outs in my public, media, and my blogs and my papers. And they've come back to me saying, Josh, we saw that you actually gave us a shout out, and like that's very unusual. Like nobody does that, but we recognize it, we appreciate it, and we're going to do the same for you. And so now that I've kind of risen into like my mid-career status, and I can start to set the tone of certain parts of the industry, I can choose, to set it for positive.
I think that's really amazing. And also at that part, like the image of you walking, like your group walking their group, it kind of like reminded me of what you said, like the nerd gang warfare.
Yeah.
It's kind of like what
Detectors were thrown down. It was just like
Yeah. It's like
breakdance battle.
coming across the opposition. But I wanted to ask a follow-up question. When you
Sure.
were talking about industry, when you made that switch from, more academia, more NASA to industry, I wanted to
Yeah.
ask more how that transition was, especially like from a scientific process perspective. Like the regulations are different. I'm assuming that changed the way you approach things. Like I'm curious about how that was.
Yeah, I think when I was like a student, it used to be a lot more siloed. You were like, or like when I was an early professor or scientist at JPL, when my postdocs would go to industry, I'm like, well, I've lost you forever. Like that's it. You're in the abyss. But now, especially post-pandemic and a lot of remote work, those walls have really come down. And so now people are just like working from home for a company, then for a university, then for like a government, whatever. And we're all just kind of doing science together. Um, so when I left JPL, this was in the pandemic in 2021 when lots of people were making changes. I wanted to be a professor, but I was also interested in hydrosat, and I asked both sides if I could split my time, and they're like, "Yeah, okay, you can do that." And so now I wear all the hats, right? And so, but at the end of the day, I'm still me. Like I'm still whoever I am, the guy who likes rock and roll music videos, the guy who loves watching basketball from the Lakers, go Knicks, I guess. Um, 'Cause but yeah. So in terms of how I operate, and so when I first joined Hydrosat, they're like, "Oh, we want you at Hydrosat." I'm like, "Okay, but I'm not a capitalist. I'm a scientist. Like, and I don't trust you guys, like, not to suppress my science." And they're like, "No, no, you can do whatever you want." I'm like, "Okay, I don't believe you, but I'll join. And as soon as like I'm proven otherwise, then I'll leave, right?" But yeah, they have Hydrosat's just like, you go be the best scientist you can be, and we're gonna cash that in. So like we've acquired companies because they know that I'm the science lead. I can talk to other chief scientists. I have all my buddies at NASA and USDA, and so we're setting up government contracts. So I can continue to be me, but I'm also pushing to make sure my data get into the hands of you guys, the scientific community. And um, and then commercially, I'm also interested in like diversity, equity, inclusion, right? So I'm like, is it just big ag, the big like PepsiCo's and those guys in Europe, the US and Europe? But what about India and all those farmers? They can't pay for it, but the government can. So now we're setting up contracts with the government to give it to the farmers of India. But what about Africa? Like the farmers can't pay for it and the government can't pay for it, but the UN can. And so now we set up contracts with the World Bank or the UN to get it through there. So I'm really trying to push out as much as possible from me as a scientific standpoint, to continue pushing the science and not be that capitalist or not be whoever the institution wants, defines you as. In fact, that was a big reason why I left NASA too, is because they were really clamping down. You couldn't say climate change, like you couldn't talk to Chinese people, like you couldn't talk to politicians. And I'm like, this is anti-science, it's racist, like, and I'm really good at talking to politicians. And so they were making me become somebody that I was not. And I did the NASA game, and I still work with NASA a lot, but there was more to me than was there, and so I found another home for myself. And really, it's about not are you an industry person, are you an academic person, but like you're a coder, you're a scientist, you're a modeler. Like, what is the best home for you to be in, and go into that home. And if it becomes not that home, switch to another home. And everyone will tell you that the path is nonlinear, and you roll with the punches and roll with the waves, and it's absolutely true. But now there's a lot more opportunity because of remote work and these walls coming down. Yeah.
So earlier you had mentioned about like some challenges that are coming with modeling how you like kill a tree in a model. And I was wondering what some of the pros and cons of different ways for doing that are in the models you've.
So like we're killing trees. All right, we got a Death Eater here. Yeah. So it's still a tricky question, right? So like Nate McDowell is like one of my buddies at DOE, and like he's like Mr. Death, Dr. Death. He loves talking about tree death, and he's part of DOE, so he works with the modelers there too. And so yeah, you can kill off trees because of hydraulic failure. You can kill off trees because of carbon starvation, or just susceptibility to some sort of disturbance like fire, or if there's some sort of insect disturbance. You know, the models are or wind throw. Um, so different models will have different ways of killing off trees. So there's not like one right answer. But I guess the point is that you can decide it, which is a lot of power and a lot of responsibility, as a modeler. Like I think a lot of you guys raise your hands. You guys are modelers and maybe earlier career, but then you guys are going to be like the main ones that are like dictating how the model functions and what goes in the model. And so I think the important thing is to know that you can choose how you kill off trees in your model, and you can know that your buddy in Australia is killing off trees in a different way. But the important thing is to make sure you check your biases as well, and to get as much data that's representative, especially in like underrepresented like the tropics, to use remote sensing data where you can get it, because then you'll have some sort of mostly systematic, consistent data. Of course, the tropics are still cloudy, so you can't see a lot. But yeah, that's changing rapidly. Yeah.
Yeah, maybe last question.
Yeah. Firstly, thanks for providing an entertainment that kept me away from the England game. That's really, really appreciated.
There's always the goal. How many people can I get them to stop doing email multitasking?
But do you see any advantages to combining solar-induced fluorescence with your thermal measurements to sort of get a better handle on overall stress?
Did you say combating or combining?
Combining.
Oh, combining.
Yeah.
Interesting you asked that question, because just yesterday we got reviews back on our paper that's doing exactly that, in Geophysical Research Letters. It's led by Zoe Perrott at UCSB, and we combine the SIF measurements with the ET measurements from EcoStress and OCO, and I think maybe Tropomi, and yeah, to really constrain exactly that question. So stay tuned. I think she's finishing up her NSF career proposal right now, and then we'll get to those last reviews, but it will be in GRL soon. Still a lot of challenges though, right? SIF is challenging, super big pixels, and then thermal super high resolution. So, it'd be great if we had higher res SIF. The Europeans are really starting to lead the way on that with Tropomi, and now the Flex mission. I just came back from Europe yesterday. Actually, I was in London yesterday, meeting with a lot of the Europeans on that one. Christian van der Tol, I was in the Netherlands on that one. And then SIF itself is just hard to translate into GPP directly, photosynthesis. Thermal to ET isn't a direct measurement, but pretty close. So you've got uncertainty there, scale mismatch, air, uncertainty propagation, and then does your air like swamp your signal? So yeah, challenges, but a lot of opportunities as well.
I've seen some companies looking to develop metasurfaces that would actually directly provide a SIP signal. It's like basically a tuned filter, so to speak.
Okay.
Which is kind of interesting, because then it would be super compact and much higher spatial resolution if they can make it work.
And you would put that like on a tower, or?
You could put that on a cube, sir.
Oh, on a cube. Okay. Oh yeah. I mean, so exactly. You can put anything on a cube, right? So that's the beauty of this space revolution. I mean, we already know V-nears, at the centimeter level, right? You go on Google Maps and all the Maxar, Vantor data is centimeter level. Now the radar data is coming down to meter level. Even the thermal data is at 3 meter. There's a company that does 3 meter thermal data, but then you don't get the coverage. But so like, for instance, we're doing the 16 satellite constellation to get it daily coverage at 25 meters for our agricultural focus. But then we talk to military with deep pockets, and they're interested in using the data for whatever they're interested in, but they're interested in like weather too. And so they're used to geostationary. And so, like, oh yeah, we're only like twice a day, but if you doubled our constellation, it would be this much money. If you tripled it, it would be this much money. And they're like, oh, that's cheap. Actually, I don't even have to request more money. Our pockets are deep. I could triple your constellation today if I felt like it. And we're like, oh yeah, do that. So it's definitely a revolution when it comes to the economics, the engineering, the technology. And so, yeah, with the students in the room who are kind of interested in combining remote sensing and technology and modeling together, lots of amazing opportunities right now. In as much as like 20 years ago, it was like if you could code in Python, there were opportunities, and like not anymore. Now it's like AI, but now in terms of like perhaps more relevant to you guys, this is a huge like opportunity that didn't used to exist.
I saw some questions here.
Yeah, maybe we'll leave it just in the interest of time because we're quite over time. So maybe they can be in touch. That's what I mentioned with Molly. So yeah,
Okay.
thanks so much for your
Yeah,
time.
for those of you online, sorry we missed that. I will try to look at the questions before, or if you can just email me, I'll respond. I respond to all emails, right, Landley? I'm like the best at responding to emails. So yeah, you can find me. My Gmail is joshbfisher@gmail.com. I also have my Chapman and my Hydrosat emails. But thanks
so
for your
much. Yeah.
attention. Hope you found it interesting and educational. Yeah.
Thank you.